Hello and welcome to homework 2, part 1. In this part of the homework, to start off, we are given a problem where we are looking at a mixing tank. And what we have here is 3 different streams going into this mixing tank. Here's our tank and this is our mixer here. And what we have here is some data for each of these streams coming in. We know the temperature of each of the streams. We know the concentration of A. So we're going to be looking at some substance A that we're going to be mixing in this tank, and we know the concentration of it in each of the streams going in. And we also know the flow rates here in meters cubed per second of each of these streams. And what we are asked to do in part 1 here is to see how the height of the liquid in the tank, the concentration of A in the tank, and also the temperature, what they are if the tank has been operating continuously stirring for a long period of time. So what we need to do in order to get there, to know these things after a long period of time, is we need to derive first the expressions of the height, concentration of A, and temperature. And then what we can do is go into Python, use solve IVP, and then put in some timestamp to see what the values are for each after some long period of time. So we'll go ahead here and start with deriving the height of the fluid level in the tank. And what we can start with here is taking a look at the volume. And if we take a look at the volume, we can just look at flow rates in minus flow rates out. And one thing I forgot to draw here is that we have some Q out leaving the tank here with a hole at the bottom, and we'll just call the cross-sectional area of this hole AH. So back to the height here, we can just take a look at the volume changing in the tank here. And we know that if we write our differential change in volume with respect to time, that's just our flow rate. So we'll have Q1, 2, and 3 in. So Q1, Q2, and Q3. And then we'll be subtracting Q out. Now from here, what we know is that the cross-sectional area of the tank, we'll call this AC. I'm not going to write it here, but just to differentiate between the cross-sectional area of the hole, we'll call the cross-sectional area of the tank AC. But the cross-sectional area of the tank times the height is obviously the volume. So we have a constant cross-sectional area because this is continuously stirred, not changing the flow rates or anything like that. So I have AC times dH dt is equal to Q1 plus Q2 plus Q3. And then this Q out here, we can actually write this down a little bit further into the cross-sectional area of the hole, so AH, and then times the square root of 2GH. All right, and then to get our expression for the differential change in height, we'll just divide over AC here. So we'll have dH dt is equal to Q1 plus Q2 plus Q3 minus AH square root of 2GH over the cross-sectional area of the tank. And this is our expression that we'll go ahead and use for the differential change of fluid level, or the height of the fluid in the tank. So we can go to next here is let's go ahead and take a look at the concentration of A. So what we can look at here is the total amount of A that is coming into the tank and then leaving the tank. So if I write something like dVCA, so basically the volume of Ca over time. So essentially the amount of Ca over time. Again, we just use a mass balance here. So I have Q1 Ca1, right, plus Q2 Ca2 coming in, plus Q3 Ca3, and then we will subtract here Q out, and the concentration of A here going out will be the same concentration of A here that is inside the tank, because we are told that it is well mixed. So if we know that we have a well mixed reactor or whatever tank we're dealing with, the concentration of A inside the tank is going to be the same concentration of A that is leaving the tank. So we just have Ca here. These are both the same. So what we can do here is our same thought process here, and take out the cross-sectional area. So we'll have AC times dH Ca dt. And I'm going to go ahead and simplify this just into summation here. So we'll go I equals 1 to 3 of Qi Cai, and then minus, let's see here, Q out Ca. Okay, and now what we need to do, we can go ahead and bring across this AC and divide it across over everything. But I'm just going to do that in this next step here. But what we need to do here is isolate this change in concentration of A with respect to time. So we need to get the height out of there. And what we can do is use the product rule here. So what we'll have is, if we see here, if we divide, I'll go ahead and divide over. We'll have Ca, doing the product rule here, we'll have Ca dH dt, right? And then plus the height times the differential change in concentration of A over dt. And then we'll divide across our AC here, so we'll have 1 over AC times, let's see here, I equals 1 to 3 Qi Cai minus Q out Ca, and let's see here, put some parentheses here because this is also multiplying that. Okay, so now what we can do is go ahead and isolate the change in concentration of A with respect to time. So we will subtract over and divide by H. So we'll have dCA dt is equal to 1 over AC. 1 over AC is going to be multiplying everything. So we'll have summation of I equals 1 to 3 Qi Cai minus Q out Ca, right? And then we will subtract Ca dH dt and then divide everything. I think my parentheses match up here. Divide everything right by H. And this is our expression for the change of concentration of A with respect to time. So we have 2 of them. Now we need to get our third one, the change in temperature with respect to time. Okay, so now for our expression for the change in temperature, the change in temperature with respect to time. So what we can do here is we're going to just do an energy balance for our system. So in minus out. And what we can do to start here is we can convert temperature into energy by using the heat capacity. So heat capacity here, if we look at as units, is usually in joules per mass times temperature. So we use kilograms, kilograms Kelvin, not kilograms temperature here. So joules per kilogram Kelvin. And if we go a little bit further here, what we can see is that if we take the volume and multiply it by the density, the heat capacity, and the temperature, that we can get to joules energy from temperature. So we'll take the volume times the density times heat capacity times temperature, and I'll just write out the units here after this equal sign. So for volume, usually meters cubed, right? Density, kilograms per meters cubed. Heat capacity, joule per kilogram Kelvin. And then temperature is in Kelvin. So meters cubed cancels out, kilograms, and then Kelvin. So what we're left with is joules here. So what we want to write our expression for is the change in volume times the density times the heat capacity times the temperature with respect to time. So let's go ahead and write that out. So I have d v rho cp and t with respect to time. Okay, now what we can do from here is we notice that if we take, just a little aside here, if we take rho times Cp times temperature, that's equal to kilograms per meters cubed times joule per kilogram Kelvin times Kelvin. And what this gives us here is joules per meters cubed, right? So what we have here is our flow rates are in meters cubed per second. So if we take this rho, Cp, and temperature and then multiply that by our flow rate, if we look at units, we will end up multiplying this by meters cubed per second, which will get us to joules per second. So let's go ahead and do that here. So we'll have the summation here from I equals 1 to 3, because we have 3 streams, and we'll take our flow rate here, so we'll do in minus out, Qi times rho Cp Ti, and then we'll subtract Q out times rho Cp, and instead of using T out here, it'll just be the same as our temperature inside the tank, because again, we are well mixed in this situation. Okay, so from here, what we're going to say is that the density and the heat capacity here is going to just be a constant. It's not going to change throughout this process. So we're just going to cancel out density and heat capacity from here. And also what we can do is change our volume here to the cross-sectional area times the height. So we have AC dHT over dt is equal to the summation of I equals 1 to 3 Qi Ti minus Q out T. Actually, I'm just going to go ahead and divide over this cross-sectional area here. So we'll divide this by AC. Okay, so now what we're going to do is use the product rule again. So what we're going to have is the temperature times dH dt. This will be, we'll add on, let's see here, the height times the differential change in temperature with respect to time. And over here, again, we will have from I equals 1 to 3, our flow rates times our temperatures, both in and out, divided by AC. So now we can go ahead, and because we have utilized the product rule, we can go ahead here and isolate the change in temperature with respect to time. So let's do that here. So we'll subtract across T, dH, dt, and then divide everything by H. So we'll have dt, change in temperature with respect to time, is equal to the summation I equals 1 to 3 Qi Ti minus Q out T divided by AC minus T dH dt, everything multiplied by 1 over H. And this is our expression for the change in temperature with respect to time. So now we have the 3 expressions that we wanted to get. Change in height with respect to time, change in concentration with respect to time, and change in temperature with respect to time. So we can now go into Python and see what height, what concentration is, and what the temperature is after this system has been operating for some long period of time. Okay, so I've gone ahead and imported in some of the parameters that we will need to solve this problem. Again, we have 3 differential equations
that we want to solve to determine the height, the concentration of A, and the temperature in the tank after a very long time. So I've imported NumPy because we'll need numerical Python to use some of its features, Plotly to plot at the end of this, SciPy integrate to solve the differential equations, and actually we'll need a root for this first part because we'll be getting initial conditions, and then from there we'll be changing, I believe we'll be changing the flow rates to see how the system evolves from there. So here I've entered in the temperatures of each stream going in, and I put it in as Tn naught, Can naught, and Qn naught, and they're all NumPy arrays. So 3 parameters in each of them, 1 for each stream. I also have the area of the hole at the bottom of the tank, which we're going to say is 0.1, and the area, the cross-sectional area of the tank itself, which we're going to say is 1 meter squared. So what we need to do from here first is define our right-hand side and solve our differential equations that we have. So I'm going to add a new block of text here. I'm going to go to define right-hand side, and we need to supply our independent variable time, followed by a vector of the dependent variables, and then we need to put in our conditions for what we're going to be used to solve this. So we're going to have Tn, or excuse me, no, we're going to have Qn. We're going to have the concentration going in, and I'm going to label these differently than our initial parameters for the streams coming in because these are going to change with time. So have Qn, Can, and Tn. Okay. Now what I'm going to do is unpack that vector of dependent variables so that we can access what we need, the height, concentration of A, and time. So we're going to go height, concentration of A, or not time, but temperature is equal to V. And now what we're going to need to use to solve our differential equations is we need to know Q out. And we can solve this because we know the cross-sectional area of the hole. So Q out is equal to the cross-sectional area of the hole times 2 times G times H. This is all raised to the 0.5 power. And, oh yeah, I need to define G here. So G, gravitational constant, is equal to 9.81. Okay, now we can go ahead and solve each of our differential equations. So our first one, we have dH dt. dt. And this is the sum of all of the flow rates minus Q out divided by the cross-sectional area. So I have MP dot sum Q in, right, minus Q out, and this entire thing is divided by the cross-sectional area of the tank, HC. Okay, and then we have dCA, so we'll go dCA dt, and remember this is dependent upon dH dt. So we have, this time we're going to be using the summation of the product of 2 vectors. So we're going to go NP sum again. This time we're going to have Qn times Ca in. If you look back at our expressions, Qa times Can minus Q out, right, times Ca, right, parentheses, and then this is divided by AC, right, and then from here we have to subtract Ca times dH dt, that's where that part comes in, multiplied by dH dt, and this entire expression here, I need 2 up here, right, so we're including here, and outside this entire expression is divided by H. Okay, I think my parentheses match up there, so it should be good. And then our last differential equation, the change in temperature with respect to time, so dt dt. This is extremely similar to this. All we're going to change, if you look back at when we derived these, instead of the concentration of A, we have temperature here, and the concentration of A going in will have the temperature of the streams going in. So I'm just going to copy and paste. So we have temperature going in, temperature, and I just put a underscore here, and T here as well. Okay, so now what we need to do here is we need to return our right hand side. So we want the height, concentration, and the temperature. And I'm going to return them in the order that I have unpacked our vector of dependent variables, obviously, so that we're getting the right values. So I have an array here. And first we'll have dh dt, right? I believe I need to move this over. So dh dt, followed by dca dt, followed by dt dt. Oops. Okay, let's make sure this runs. And what we need to do is, we have said that we are looking for the height, concentration of A, and temperature of this tank. If we keep these flow rates, and we want to see this over a long period of time, so essentially it's going to reach some steady state. So what we can do here is that what we can see is that if all of these derivatives here, dh dt, dca dt, and dt dt, if all those derivatives are equal to 0, they're not changing, then that is when we have reached some steady state and we can get those values. And what we're going to do is we're going to use those steady state values to use them as the initial conditions when we, let's say, change one of the flow rates, or maybe we change one of the temperatures of the streams going in. We heat one of the streams up, or we cool one of them down, and we can see how that affects the tank over time. So we can actually use a root solver here. So let me delete. So now what I'm going to do is go ahead and use the root solver, and I'm going to create a function, create a function called lambda. And we want this to just take in a vector of our height, concentration, and temperature. And what that's going to do is call then the right-hand side function that we have up here. So let's go ahead and do that. So use our root solver. We're going to create a function, lambda, and we're going to have v as our vector of height, concentration, and temperature. And it's going to call in our right-hand side function. And then we can supply what we have here. So for time, it's not used anywhere in these expressions, so I'm just going to put 0 for it. It doesn't really matter. We'll have v, our vector of unknowns, and then we'll supply our initial temperature, concentration, and flow rates into the tank. So Q naught, Ca, N, and Tn naught. And then what we need to do in order for the root solver to actually run is supply an initial guess. So we're going to have an array here, and we can guess somewhere in between. So it goes 0.4, whoops, 0.4. For our concentrations, we'll guess, again, somewhere in between, so like 0.5, right? And then for our temperatures, again, somewhere in between, we can put like 70. Close this out and make sure it runs here. And what this tells us here, for our solution here, first of all, our x here is our values. So 9.99 meters is how tall our tank is, or the fluid, so that's the height. Then we have our concentration here at 0.4286, and then we have the temperature looks like at 81, 82, or no, yeah, 81. So we can see that this is true because what we can see here is that these functions are all essentially zero. So our dH dt, dCA dt, and dt dt have all been driven to zero. So we are at some steady state. Again, zero on this first one, very close to zero here for the concentration, and very close to zero again for the change in temperature with respect to time. So what we can do is we can go ahead and grab this solution. So we'll go solution, and then we can use this. This will complete part one because we now know the high concentration and temperature. Actually, this tank has been operating under a long period of time. But in part two, what we're going to do is use these as initial conditions, and then we're going to alter some of the parameters coming into the tank, and then we can see how that changes with respect to time. But that will do it for part one. Thank you for watching.